Hi, everyone. So I'm just going to go over this one practice test today. Hopefully this will help you in preparation for your test. So I'm going to kind of go semi-quickly through these. I'm assuming that you have a background on these, that you have some idea what's going on in each of these questions. So I won't take, 10, 20 minutes on each question. All right. So number one, right, it says for this reaction, what is the equilibrium expression, Kc? So you know that your equilibrium expression, right, when we base it off of the concentrations, is going to be products, concentration of products to their respective coefficient over reactants to their respective coefficient, right, as a power. Coefficient being these twos, right? So that's going to be equilibrium. Now, we should have our products to be CoCl2 and Cl2. Just to double check, both of these are gases, right? We only include gases. We don't include solids or liquids in these equilibrium constants. So CoCl2 and Cl2 will be in the equilibrium expression. So will O2 as a reactant. This CCl4 will not. And so the answer is going to be C. Right, where we should end up getting or you will end up getting CoCl2 to the second power, right? Because it has a coefficient of 2, Cl2 to the second power because it has a coefficient of 2, right? And then over O2, which has a coefficient of 1. So it is to the first power. All right, next two, it says, which of the following units are written correctly? So joules is not in newtons per meter squared. Joules is equal to newtons times meters. This comes from the work formula of force times displacement, where displacement is in meters. So joules are in newtons times meters. Pascals are in newtons over meters squared. Now, if you turn these into their respective SI units, right, Pascal will end up being, so if you turn Newton into an SI unit, or into SI units, you're going to get kilograms times meters per second squared, right? Force is equal to mass times acceleration. And then SI, we just use kilograms instead of grams, right? So then this is times 1 over meter squared. So for a Pascal, it has SI units of kilograms over meters a second squared, right? One of the meters cancel out here. And then joules is going to be kilograms times meters over second squared times meters, right? From the first formula I wrote on the left, this is kilograms times meters squared over second squared. So D is the only one that's written correctly, right? You'd get past on the test, right? I would get past these three, and then I would just say it has to be D since those are wrong. All right, 3, it says, which of the following is the strongest base? So you have a bunch of things with nitrogen except for the E. So why is nitrogen a good base or a strong base? It's not because nitrogen is unstable. It's because nitrogen has the lone pair on it, right? And nitrogen is not as electronegative as something like oxygen. And so nitrogen is much more likely to share its lone pair than something like oxygen. And so even though, right, nitrogen is not a strong base, right, we're talking strongest base amongst these in this react or amongst these choices, right? None of these are a strong base. None of these are just going to give off a hydroxide, right? But which one is the strongest base? So we're going to be looking at the ones with nitrogen, right? So this hydrogen peroxide doesn't have nitrogen. It's not going to act as a base. It has 2 oxygens. It's like 2 OHs that are stuck together pretty much, right? Ammonia is NH4 plus, so this cannot act as a base because nitrogen can't have 5 bonds, can't gain another hydrogen. Ethylamine has this NH3 like that. Aniline is going to look like this. And hydroxyamine going to look like that. So which one of these are the strongest? Well, it's going to be, I'm going to tell you the answer and I'll tell you why after, but it's going to be ethylamine. So in B, nitrogen has this lone pair. Now this lone pair is next to a bunch of pi bonds. I don't believe you really learned about conjugation yet, right? But when it's near all these pi bonds, this lone pair is what we call conjugated, right? And so when this lone pair is conjugated, it's in a p orbital and it gives the molecule extra stability. Now, because this lone pair is next to this system of pi bonds, right, it's going to be less reactive, right? It's going to doesn't want to give away this lone pair, right? If it gives away the lone pair, then it's giving away some stability. A way you could think about it is that this lone pair is having electron density sucked into the ring. And so it's losing electron density, right? So it's going to be a weaker base for that reason, right? It's a stronger base when you have a higher electron density in some place, right? So this is just from basic electrostatic charges, right? The more negative something is, the more likely it is to take something positive, right? Over here on A, right, it's next to O. And so you can imagine, right, it's pulling some of the electrons towards the oxygen, right, a dipole moment. And so there is a less electron density on the nitrogen, right, as opposed to the ethylamine. So the ethylamine has the most electron density on the nitrogen, right? And so this one is the strongest base. All right. So we'll go on to the next one here. Number 4, it says a gas produced by reaction is collected over water at 720 millimeters mercury at 23 degrees Celsius. What is the pressure of gas collected in millimeters of mercury? So we're going to essentially take this and subtract the pressure due to water. So when you collect over water, right, you're going to get the gas pressure, right? So the total pressure is defined by the partial pressures of each gas, but you also have the partial pressure of water, right? From the water evaporating into the system, right? So I'm going to subtract the pressure of water here to get the pressure of the gas. Now, let me find if we have a table here. We do not. Maybe we don't even need one. Oh. Oh, yeah. Okay. Never mind. So, yeah, we don't need one here, right? So if you look at this, right, if I have to subtract the water here, we're going to, if we plug in some stuff, we get 721 mmHg minus the pressure of water, right, in mmHg is equal to the pressure of gas. Now, you can see that it's 721 minus something, right? So it can't be bigger. It can't be the same. And I can tell you it's not going to be 21. So that's just too low. The pressure of water is usually, when I remember like the 10 to 30 range, it's probably closer to the 20-ish range. I really don't remember. But it's going to be 700. So that is the answer to number 4. All right. 5, it says, which of the following is not true for a real gas? Relatively high pressure and low temperature. PV over nRT is not equal to 1. So we're seeing which one's not true. So this one is true, B, right? Because your PV equals nRT expression no longer holds, right? And so you're going to have to use the van der Waals equation instead. And so the PV terms change. P and V terms change. Relatively high pressure and low temperature. So this is true for how you would find a real gas, or right, is at high pressures and low temperatures, it's going to behave more like a real gas. C, inelastic collisions between gas molecules. This is also true for a real gas, right? So the ideal gas, you assume that all energy is conserved. So when particles collide, the energy is conserved. The kinetic energy is completely conserved. However, that's not true. You end up getting inelastic collisions in a real gas. D, it says attractive forces between gas molecules. That is also true, right? So molecules will be attracting each other. So that changes some of the dynamics of the system. And then E is the only answer that's left, right? And if you look at it, it says gas molecules occupying a negligible volume, right? That's not true. That's for an ideal gas. That's the assumption of an ideal gas, that volume takes up no space, or gas particles take up no space, right? And so when you change the V term in the van der Waals equation, right, it counts for particle volume. 6, it says, what is the height of a column of liquid water in meters required to exert the same pressure as 2 meters of liquid A with this density? Okay, so if you have a column, right, you know that the pressure is going to be equal to rho G H. Oops, we don't use rho in this class. We use D. Rho for density, but I forgot that you guys use D. So dgh, right? Now for this first column, right? And again, this is where it's maybe wondering, well, okay, if you do the units aren't going to be pascals. So because you're not doing it over an area, you're doing it over a column, right? You're doing it over this infinitely small kind of tube. And so you end up just getting this height term, which gives you the meters, right? And you end up not really caring about the area at all for these types of problems. So the units will not be the same as pascals, right? Just keep that in mind. All right, so so I'm not going to use units here. But for pressure, right, we get pressure is equal to, for this column that we have the information on, right, this is going to be equal to the density 1.5 times the height of the column, right, which is 2 meters, times G, right? We know G is 9.8. You're going to see why I leave it as G. You can multiply it or keep it there. It's going to cancel out for the other column. So this is going to be 3G. Now, if I go, and so I should label this, I'm going to call that the pressure of A. Right now we want the pressure of water. So what is the height of a column of water to exert the same pressure? So we know that the pressure is the same. So the pressure of water is 3G, right? You could plug in a number there. I'm just choosing not to. And the reason is this is equal to dgh, right? So the pressure of water, sorry, the density of water is 1, right? 1 gram per milliliter or centimeter cubed. And then gravity is still the same. And then the height is what we're looking for. So these G's will cancel out. And then you end up getting the height is equal to 3. And that's it for this problem. So you plug into this density times gravity times height, right, to find the pressure, and then you can solve for what the height of the water column would be using the density of water. All right, 7, it says pure nitrogen gas in a lab flask has a pressure of 1 atm. If the oxygen gas is added to the flask until the number of molecules of oxygen is twice that of nitrogen, what is the total pressure of the flask? Assume constant temperature. So we reread this really quick. Pure nitrogen gas has pressure of 1 atm. Oxygen gas is added to the flask until the number of molecules of oxygen is twice that of nitrogen. What is the total pressure of the flask? Okay, yeah, so we know that the partial pressure is equal to the total pressure is equal to the combined partial pressures. Like that. Now, we know the pressure of nitrogen is equal to 1 atm. Now it says if oxygen was added to the flask until the number of molecules of oxygen were twice that of nitrogen, what does that mean? What do you get out of that statement? So what do you get is how many moles of oxygen compared to the moles of nitrogen. So as I have stated, right, a mole is just having 6.022 times 10 to the 23rd, something, an Avogadro amount of something, right? So just has as a dozen eggs is 12 eggs, right? A mole is an Avogadro number of something. So the number of molecules is linked to the number of moles, right? Now, if you have twice as many molecules, right? We're talking molecules, not mass, right? But if you have twice as many molecules, you will have twice as many moles. So I have from this statement is twice as many moles of oxygen. Two times, oops, I definitely wrote that wrong, but I have twice as many moles of oxygen than I do of nitrogen. No, I did not write that wrong. So, right, I have twice as many molecules of oxygen because, or moles of oxygen, because I have twice as many molecules of oxygen, right? Moles and number of molecules are interlinked. Now, what is moles interlinked with? It's interlinked with this pressure, right? They're proportional. So the more moles you have, right, the more pressure, partial pressure you get. So assuming that the volume is the same and everything else is constant, and that oxygen will also provide the same pressure per mole, right? We can say that the pressure of oxygen is 2 times the pressure of nitrogen, right? Since there's twice as many moles of oxygen as there are with nitrogen, and the pressure of nitrogen is linked to the moles of nitrogen, right? You're assuming a constant temperature and volume, right? Volume because it's a flask. Temperature, there's no heating. This is 2 times 1, which is 3, oops, not 3, which is 2 atm. And then when you add these two up, you get 1 plus 2, which is 3 atm, right, for the total. So number 7, right, you're using your partial pressures and essentially comparing the moles of each of these. All right, we'll go on to number 8 here. 8, it says a beaker contains 1 molar HF, not including water. What species would you expect to be in the highest concentration? So HF is a weak acid because fluorine is very electronegative. It's not that as polarizable, right, compared to something like fluorine, bromine, or iodine. And so when HF associates, it's a weak acid. It's not a strong acid. Now, you can see here, right, that it gives you an H plus. Now, a more accurate way to write this would be like this. right? So we can see that this HF turns into H3O, and HF and H2O turns into H3O plus and F minus, right? You do an acid-base reaction. So it's clearly not OH, right? You're not forming a hydroxide anywhere. Now, is it H3O plus, F minus, or HF? Well, it's going to be HF because it's a weak acid, right? So it's a weak acid, which means it dissociates very little. Usually. This is usually true. It's not, usually it's negligible, right? Compared to, so the amount of hydrogen, right, and fluorine that are made, or sorry, I should say weak acid conjugate base, right, to hydrogen that's given off, usually it's negligible compared to the amount of just normal acid that you had. Now, not always negligible. So that's why I said usually true being the very little part. So, and I should say almost negligibly. Maybe that is a better way to say it. So that's usually true. And so it's going to be A, right? Where most of this does not dissociate. Most of it will not. And so it's going to be HF, right? You're going to get the most of HF in the solution because the equilibrium is favored to the left. If you want to look at this in terms, equilibrium constants, right? Your Ka is much less than 1. It's like 10 to the negative 9 or something. So the forward reaction is not favored. All right, number 9 is next. So it says identify the Lewis base in this reaction. Right, so if we're looking at this, right, can draw some electrons there. Essentially what you're looking at is who is giving away their electrons and who is accepting them, right? So Lewis acid-base definition goes with the definition of right, electron movement. So Lewis bases are electron donators, right? While Lewis acids are electron acceptors. So Bronsted-Lowry definition, right, it has to do with hydrogens moving around, right, protons. Lewis acids bases are with electrons being moved around, which is a more general definition, right? So Lewis acids encompass Bronsted-Lowry acids bases and Arrhenius. And then Bronsted-Lowry just really encompasses Arrhenius definition as well, right? So Lewis is the most broad. So here, right, the water has these two lone pairs, right? Now this SO3 spoiler does not. And so the water has to give up its lone pair, right? So the water is going to be the Lewis base, right? While the SO3 is going to be the Lewis acid. Now, if you don't know the structure of SO3, you don't have to, right? Because I can ask, well, is it even possible for oxygen to accept any electrons if sulfur had any, right? So you know one of these has to be the acceptor, assuming this reaction is true. And so oxygen, right, can't take any more electrons. It already has 8 electrons, right, in its shell. It has 2 bonds with hydrogen, right? That's 4 electrons. And then it has 2 lone pairs. It can't just take another. It's not one of the exceptions that can have an expanded octet. And so oxygen cannot be an acceptor of those extra electrons, even if sulfur had it, which shouldn't. So sulfur has to be the acid here, assuming this reaction is true, right? Where it's accepting those electrons. All right, number 10, it says choose the Bronsted-Lowry acids and bases in the following equation. Oh, I lost my mouse. Where did my mouse go? Oh, there it is. So easiest way to do this is just look where the hydrogen goes. Right, so you have this H3, right, H3O plus, and you have this H2O, right? So you know that this is the acid and this is its conjugate base, right, because it loses the hydrogen. This N3 is the base because the other one's the acid, and this is the conjugate acid, right? You could also see that a hydrogen was gained, right? So this had to be the base on the left and the acid on the right. Now, now we just have to look for the right answer. So the acids are H3O plus and HN3, and the bases are the other two. So it's going to be A. Easiest way to do these Bronsted-Lowry ones is, again, just look where the hydrogen goes and label it accordingly. So the hydrogen was on the left, right, and it loses it on the right, then the acid is on the left, right? So label your acids and bases first, and then just look at the rest. Also to note, right, if you have an acid on the left, you should have its conjugate base on the right. So consider the reaction profile plotted for A versus B at equilibrium is K is small or large, and the reactants or products are favored. However, at T equals 0, Q is what, and the reaction shifts towards what. All right, so let's figure out the Kc first. So it says at equilibrium. So at equilibrium, right, over this long period of time, it reaches this this stable state. So you can see here, right, again, let me just write K for this. K is going to be the concentration of B, right, products, over concentration of A, your reactants. They're both to the first power. So B is larger than A, right? So since B is bigger than A, right, it's going to be small. So small, right, because it's a, oh, whoops, large. My bad. Large because, right, you're dividing a larger number by a smaller number. So that's the consequence of the division here. So if A is larger than B, right, then it would be small. I think they're meaning less than 1. So, and the products are favored, right? We have more B than A. Now at T equals 0, Q is what? Right? Q is the concentration of products over reactants at some time, right? And during the reaction. So over here, right, you can see that I put this not, right? So for initial, it just depends where your starting point is when you measure this Q. So for this first one, right, the B is at 0. So you get 0 over 1, which is just 0. So the answer is 0. It would be approaching infinity if the bottom was 0, right? If it was the other way around, you would get 1 over 0. Now that's undefined, but you would say as it goes to 0. So that's more math jargon I won't really go into any limits. But 1 over 0 will basically be infinity. It's 1 over an infinitely small number. Think of it like that. So 1 divided by something infinitely small, if you plug that into your calculator, you get a very tiny number. So this is approaching 0 for Q, and the reaction is going to shift which way? Towards the reactants or products, right? Well, it's shifting towards the products. You can just see from this chart, right? Reactants go down, A goes down over time. Also, you can do a Q comparison, right? You can say that Q is less than K, right? So Q shifts to the right. And so now it's just a matter of looking for the right answer here. Large products, 0. Okay, so B. And that is it for 11. All right, so we're on to number 12 here. 12 says, what statement describes pKa and pH the best? All right, so Ka is a constant, right? Depending on what the weak acid is, Ka is some constant that describes to you, right, how much it dissociates essentially. So it's an equilibrium constant, right? pH, right, is dependent on what is the concentration of hydrogen in a solution. So pKa, right, the way to think of the P is taking the negative log of something, kind of like an operator. So right, pKa is the negative log of Ka, right? And this is also a constant. It doesn't change, right? If Ka is a constant, then pK is a constant, right? pH changes depending on what the concentration of hydrogen is, as I said, right? And so I guess let's read these answers first. So it says pK is a constant for a particular reaction and pH is concentration dependent. All right, so it's going to be A, where pK is a constant again for some particular weak acid, right, for a particular reaction, and pH is concentration dependent. pK and pH do not both correlate with acid strength, right? Those are the pK is the same always. The pH values are tabulated for weak acids. It's not true, right? pH changes. pH is the measure of acid strength. No, that's not true. And E is not true. All right. 13, it says citric acid is a triprotic acid. One of its corresponding ions is HC6H5O72 in solution, which reaction shows this acting as a base in water, right? So if you get some base, right, usually it has some sort of minus, right, plus water, you're going to get the base with a hydrogen plus OH minus, right? So it's not B, right? We should have water on the left side. It's definitely not E, right? We shouldn't get H3O plus on the right. And so it's A, C, or D. And now we're just trying to see which one is correct. All right, so if we look at A, you go from one H to two H's, right, out front, right, indicating usually the H out front indicates the acidic proton. And so the answer actually is A, right, where it gains one H, right, from the water. One of its core, yeah. So it gains one H from the water. It's not going to gain two in one go. So it's not D, right, where it goes from H to H3. You can even double check, right? But if you count your number of atoms, it's not equal on both sides. The right side has one more H atom than the left. And then it's not C because this indicates that it's losing this H and it's acting as an acid. And this is not even balanced, right? So if you, again, were to check the balance here, your hydrogens on the left are going to be greater than the right. All right, that is 13. Number 14, it says if 1 molar solution of acid has a pH of 2, what is the percent ionization? So what you want to do is this is from our discussion worksheet, right? So the percent ionization is the concentration of hydrogen, assuming that, right, the concentration of the solution is sufficient, right? If it's so dilute that this is negligible, then you can't do this problem. So if the solution is so dilute, right, that you don't know if your H plus is coming from the water or the acid, then you can't do this problem. So H plus, concentration of H plus on top, right? And then you get the concentration of the acid. Now, this is the initial concentration of the acid. Right, that's why I put this little zero here. This zero just means not, or that's usually how it's referred to, right? So HA not, the not meaning initially. So, right, some other places you may see this is like physics. So V naught is a common subscript, or VI sometimes they use instead as V initial. I know V naught is usually used though, or often used at least. All right. So all I have to do is plug in these quantities, right? I know that H plus is equal to 10 to the negative pH, right? This comes from the negative log formula. You can't undo it. I would personally recommend just going over your logarithm rules. If you have any questions about it, right, shoot me an email. But I would recommend going over your logarithm rules and just knowing how to reverse it, right? I don't think it's worth memorizing all these formulas just for the sake of memorizing. So if you understand the math, right, it becomes significantly easier to memorize less of these, or just to get these answers right. So this is 10 to the negative 2, right? Now just plug it in. 10 to the negative 2 over 1. Oh, and I totally forgot. Times 100%. And then you just plug it in. So you end up getting 1%. And that's your answer. All right. Next is going to be, another way you could calculate percent ionization is going to be the conjugate base, assuming that you didn't have any of it in the water before, right? Over the concentration of the acid initially. That's probably a more accurate way to do it because you don't have to account for or even worry about the autoionization of water in that case. So that'd be a better way to do it. You're just not given that number here. 15, it says, what is the molar mass of a gas if 10 grams of it occupy 4.48 liters at 273 Kelvin and 101.325 kilopascals? Where's my mouse? There it is. So, all right, so what we're going to do here is use PV equals nRT. So we have PV equals nRT, right? Why are we using this? Because we're able to relate moles to molar mass, right? And we have the grams. So first I need to convert this into ATM. This is about 1 ATM, so I'm just going to do that. So we have 1 ATM here times 4.48 liters. We're going to make sure it's in liters and in ATM. This is N, what we want. And then we use R, 0.0821. And then temperature is 273 Kelvin. Right, and then you solve for N, you just divide both sides, right, by 0.0821 times that. And you get N is equal to 0.1999. I'm just leaving the decimals just so I don't have any rounding errors. Now I can convert moles into molar mass, right, because I have the grams. So I just do 10 grams divided by 0.1999 moles. And you get 50.0. I think it's your C. All right, number 16, it says, what is the pH of a 1 molar solution of pyridine? All right, so pyridine looks like nope, I'm missing a side. 1 second. Okay, it's supposed to be a hexagon, but I, so, and then it has alternating bonds like that. So pyridine is going to act as a base. So it's not going to be A or B, right? And so if you have a 1 molar solution of pyridine, you should get some basic solution. Now it's definitely not going to be 14. That's just way too high. But the question is it 8.82 or 9.59? Right. So you should have the KB of pyridine somewhere when it's given. And so pyridine has a KB, just looked it up, 1.7 times 10 to the negative 9, right? This will be given. And so this does an acid-base reaction like this plus H2O. That becomes positive, and that's it as an OH minus. All right, now what we can do is do an ice table. So if I have pyridine, all right, I'm just going to do it over here. Pyridine is my weak base. So I start with 1 molar. I start with, it doesn't really matter how much water I have. Right, we don't really consider that an equilibrium constant, or we don't at all. So we don't really care about how much water there is. It's in a solution of water. There's a lot of water. So I don't really care about that. This pyridine, we start this protonated pyridine, we start with nothing, and same with the hydroxide. The change, I'm going to say this is minus X. I will say that this is plus X and plus X, right? And so this is 1 minus X, this is X, and this is X. All right, now you have a formula similar to the Ka1, right? Except it's the concentration of hydroxide squared over the concentration of base. Minus the concentration of hydroxide. All right, now I know the concentration of hydroxide, or I denoted it as a variable here, right? The concentration of hydroxide is X. Now, why, just as a quick thing, right? Why am I allowed to do this ice table molarity? I'm allowed to do this ice table molarity because the volume of solution is not changing, right? So same thing can go for gases, right? With ATM, right? And partial pressures and stuff, right? If the volume of the container and the temperature is not changing, right? The partial pressures are linked to moles, right? Of something. The concentration here is linked to moles, right? And if the volume is not changing, then we don't really have to worry about any weird things happening, right, with our math. So you're allowed to work in concentration here instead of working with moles on your ice table. I believe there's a problem on a different test, or maybe it's on this one, but you have gas A turns into gas B and C, and you can work in ATM, right? It's asking what's the partial pressure of B and C, and you're allowed to work in ATM because the volume is held constant and the temperature is held constant, and the R is constant, right? In PV equals nRT. So you don't have to convert anything to moles because you also can't here. All right. So this KB, I'm going to just rewrite this right over here. This is the concentration of the base, and this is the concentration of OH minus, right? That's the X. So this is X squared over 1 minus X minus X. This is X squared. I'm not saying that this is negligible because quite frankly, I don't know if it is. For fact, I don't know if it is. You can qualitatively guess, right, that this is going to be pretty weak since it's 10 to the negative 9, right? And so you're not going to get that much hydroxide formation. So you could say that this is negligible. I'm going to use the quadratic formula for 2 reasons. One is I just want to make sure I get it right. I doubt that it's going to be that big of a difference though between either of these. Like, so if you use the estimation, if you got like 9.3, then you would have had to use the quadratic formula, but you're probably going to get like 8.8 or 9.61. It's going to be pretty close. I don't know. So you can use it, but I'm doing it here just to make sure we get the exact number, but also to show you, right, all of you out there, right, how you can use a quadratic formula, because I know a lot of you are struggling with that. So this is going to be 1 negative X minus X on the bottom here, right, is going to be 2X. So yeah. And then I can go ahead and solve for X here, right? KB is some constant. Now, what I do not recommend ever doing, actually, even if you end up getting this in terms of like a different number, like, I don't know, 1.5 times 10 to the negative 3, I recommend just leaving it as a variable. I'm only doing the 1 here because it's easy, right? The 1 makes it easy. You could more generally write this as B, right? Or A, or whatever you want, right? Just to make your life easier when you plug in numbers. What will eat your time on a test is plugging in a whole bunch of numbers for KB and everything else and multiplying them all at every single step, right? And it becomes extremely hard to keep track of the numbers, which is why I'm not going to do it here, right? Like, let's say if this was instead, I don't know, 2 times 10 to the negative 3, right? And then you're multiplying it by this, right? When you cross multiply up, it's too much to keep track of, right? It's going to be extremely difficult to just write down all the numbers in a timely manner, especially that part, and keep track of everything and get it right. So I highly recommend working with variables. The same is true in classes like physics. I always recommend working with variables. It will make your life significantly easier. It's not something that you're not used to, right? But it is easier. It's just significantly easier to work with. All right, so I'm going to solve for X here, right? I'm going to just rewrite this like that. So if I cross multiply, I get KB times 1 minus 2X is equal to X squared, right? This is the same as KB minus 2KBX. KB is a number, right? It's a constant. I'm just not plugging it in because I don't want to write it over and over, and I don't want to lose track of anything. It's X squared. Now, this is a quadratic formula, right? So we're going to go back to algebra here. Right, make sure you solve a quadratic formula, you get all your variable that you want on the same side, right? KB is a constant. I don't care about it, so I don't have to worry about it. It's just some number, but I need all my x's on the same side. I like to keep the biggest degree positive, it just makes it easier plugging in for me. But either way works. You could move the x squared to the other side. I'm going to move everything to the right side. So this is going to be x squared plus 2kb times x minus kb is equal to 0. Right now, the quadratic formula, just recall. Right, if you have some variable in this form, in standard form, x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. If you don't know it, you have to memorize it. Or you could memorize a more general form. However, I think that's just harder and not as useful. So memorize the quadratic formula if you don't already. Now, this b, right? This is b, this is c. Let me do a different color here. So that's b, that's c, that is a, right? Now what you do here is just plug everything in, right? So this is minus 2ab plus or minus the square root of 2kb squared minus 4 times a times c all over 2 times 1. Oops, c is negative kb, my bad. Right, because kb is the constant in this quadratic formula. All right, now you just plug it in, right? So I'm just going to plug in into my calculator in one step, right? Anywhere that there is a kb, I'm just going to put 1.7 times 10 to the negative 9. If I can find it. Give me 1 sec, I'll plug this in and show the final result. All right, so if you look at this, right, I have 2 answers because of this plus or minus. Now you're only allowed to have 1, right? So the answer is the positive 1. You can't have a negative concentration, right? X stands for the concentration of hydroxide. So the negative 1, we ignore. So now that we have the concentration of hydroxide, right, we found X, the concentration of hydroxide. Right, in an acid, you would denote X as the concentration of hydrogen. But now we have to find pH. So to find the pH, right, we do pH is equal to 14 minus POH. I know POH is equal to the negative log of the concentration of hydroxide. And I get pH is equal to 14 minus the negative log of 4.12 times 10 to the negative 5th, right? Or pH is equal to log 9.61. Now, if you're looking at this, where is it? Yeah, it's going to be this one. Funny, I actually guessed the number right. So what happened here is in the answer, the person probably ended up using the approximation, right? So it's off by 0.02, right? And so the approximation is where you would just ignore this X here, which simplifies the problem a lot, right? So if you ignore, sorry, not that X, you ignore this right here. And so if you go ahead and ignore that, right, this whole thing becomes significantly easier. Oh no, I just realized I did not mean to do that. Okay. I accidentally double plugged in the minus X here on the bottom. Oops. So this is not right. What happened? So I accidentally double plugged in this. So it should just be 1 minus x, right? It's the base at equilibrium. So this could say the initial concentration of the base. But let me fix this really quick. So that should just be minus x. That's going to be minus x. So the 2's just go away. I'm just going to have to re-plug this back in. Oops. Two. All right. Okay, now let's see how that changes our answer. All right, well, it actually doesn't. So the numbers still end up staying the same because the KB is so small. So doesn't really change it, but that was mathematically wrong. So yeah, the numbers still stay the same here. But if you use the approximation method where you just ignore the OH over here, right, then it makes it significantly easier, right? You just multiply up here, and then you take the square root of both sides. And that would give you probably the 9.59, right? And so it is pretty much the same, right? So you can usually use the approximation, not always, but this is how you use the quadratic formula, right? The approximation, you just ignore this minus x, and then it becomes a lot easier. All right. Go on to number 17 here. It says the hydrogen sulfite ion HSO3 has this Ka. What is the equilibrium constant for the following reaction? Right, so for this equilibrium, right, this Ka value, that's specifically talking about right HSO3 dissociating into H plus or H3O, whatever you want, plus SO3 minus, I forgot minus sign here. All right, this has a Ka of 1.0 times 10 to the negative 7th. Now water is the other thing here, right, that's going on. So you have to consider this equilibrium constant, otherwise you won't be able to solve this. So this water has a dissociation like this, and this equilibrium constant, you should know, is Kw, right, 1.0 times 10 to the negative 14th. And so now we just have to look at these equations and see how we have to add them up, right? So I'm going to have to reverse this one, right? Which means the Ka is flipped, or we did invert the Ka. Or take the reciprocal. I think that's a more accurate way to look at it. So that's 1 over Ka, right? Because I have to reverse it, and then this water just stays the same, right? Now, when I add these up, right, things will cancel out. And so we get the proper equation, but now with your equilibrium constants, remember that you do not add them, you multiply them. So I get 1 over Ka, right, because I reversed that first one, times Kw, and then I just plug in the numbers. So 10 to the negative 14th, 1 times 10 to the negative 14th, over 10 to the negative 7th, 1 times 10 to the negative 7th. I just didn't want to write it in. And then those cancel out, and we get left with 10 to the negative 7th. So the answer is B. All right, just remember to write out the equation, right? And then see how you have to change it, right? Whether you reverse it, whether you multiply it, or when you multiply it by something, 1/2, 3, whatever, you raise Ka to that power, right? So if you multiply the whole thing by 2, you raise Ka to the power of 2 to find the new equilibrium value. and so on and so forth. So that's number 17. Number 18, it says fill in the table below by identifying whether a solution of each of the following is either acidic, basic, or neutral. So this BaClO4 right? Is it acidic, basic, or neutral? And same with this NH4F minus. So how you do this problem, right, is you look at these, look at the ions in solution, right? So you have barium 2 plus, and you also have ClO4 minus. Now, if these were to react with water, right, I would get barium hydroxide. You're not going to get barium hydride, right? Why? Because, or BAH or BAH2, right? Because H has a positive 1 charge. So you're not going to get that. This is going to be BaOH2, barium hydroxide, or HCl4. Now you should know, right, that HCl4 is a strong acid. So this just doesn't even form. Right, so if that doesn't form, right, because it's a strong acid, if it formed, it would just redissolve. This barium hydroxide, however, is not a strong base, right? It does not completely dissociate, so this will form. So if this forms, you get barium, right? That's going to react with water to form this. This is not balanced. I will not balance it because I don't need to serve this point, right? The point being that we get this H plus on the other side, right? I mean, there, now it's balanced. But you get this H plus on the other side. And so this is going to be acidic solution. All right. Next is NH4F. All right, so for this next one, if you look up the Ka values, should be given. The Ka of NH4 is about, it was like 10 to the negative 10th. Then the Kb for fluorine, let me write this, is about 10 to the negative 11th. And so if you just look at the constants, right, you're able to tell that fluorine is less likely to act as a base, right, or less strongly acting as a base than this NH4, right? It's a lower power. And so this solution will be acidic, right? Because ammonium is more, acts more of an acid than fluorine does a base. If they were the same magnitude, then we would say neutral. So I looked up the pH, it's about to be like 5.5 or something. I think it was like 5.5 or 6 point something. All right, next is 19. So 19 says neon and argon gas are at 298 Kelvin. Given this information, fill out the blanks below. So what is the root mean square velocity of neon gas? Right, so if we pull up a periodic table, give me 1 second here. This should be good enough. So neon is 20. This was around at 20. So the root mean squared velocity, right, is going to be in this formula. You take the square roots, 3RT, where R is 8.314. T is the temperature in Kelvin. M is the molar mass in kilograms per mole. So this is 3 over 8.314 times the temperature, which is 298, over 20, right? I'm just going to round here. 20 times 10 to the negative 3 kilograms per mole, right? It's 20 grams per mole. So to go to kilograms, right, you're going to get a smaller number. So I'm dividing it by 1,000, essentially. Now I go ahead and plug this in. And then this is going to end up being 609.62. So closest to 607. Maybe it was my rounding. And that's it. Next is the kinetic energy of argon gas, right? So the kinetic energy is equal to 3/2 kBT, where KB is Boltzmann's constant. So the kinetic energy is equal to 3/2. The temperature is the only thing that changes, right? It's 298 Kelvin. Boltzmann's constant, I think it's 1.68 times 10 to the negative 23. Somewhere around there. No, 1.38. That's close. So this is 1.38 times 10 to the negative 23. And then this is equal to something when you plug it in, right? And so this just comes down to really memorizing the formulas because you're not going to derive them on the spot. So if you know these, you should be solid for these types of questions, right? And then this is 6.17 times 10 to the negative 21. Now, this is for every, this is the average energy per molecule of gas, right? So again, this is kinetic energy per molecule. So just keep that in mind. So if I want to convert this into moles, right, joules per mole, so this is going to be this number that I just got, right, times Avogadro's number, right? That is going to convert this joules per molecule, or I guess I can just say atom here since it's just argon, joules per atom to just joules, right? So this is number of atoms for Avogadro's number. Let me move everything over. Atoms for Avogadro's number is the unit, right, for every 1 mole. So that's 6.022 times 10 to the 23rd. And then I'm just going to plug it in. This is 3,714.7 joules per mole. So the answer is the last one again. All right, next it says the argon to neon ratio of effusion time. So for this effusion time, you can use this formula. The rate of effusion of A to the rate of B, so this ratio is equal to the square root of the molar mass of B over the molar mass of A. So you just plug these in, right? So argon to neon, so argon is A, right? So neon is 20. And then argon is 40. We're just rounding here. So square root of 20. And we're just kind of getting some rough numbers here. We don't really need the exact answer, which is going to be 4.4. Oops. Wait a second. Nope, sorry. Square root of 1 over 20, or 1 over 2, not 1 over 20. 1 over 2. All right, square root of 1 over 2. is 0.7. 0.707. So that's going to be this second one. All right, now for this next one, 20, it says circle the molecule that is more acidic, right? So the molecule that forms the more stable conjugate base is going to be the one that is more acidic. So if you have these conjugate bases, right, this would be an N minus, this would be an O minus. Now, oxygen stabilizes the negative charge better due to its electronegativity being higher. So this one here, this OH, is going to be a more stable conjugate base because the oxygen is a more electronegative atom, right? And so the answer is CH3OH. Looking at the atoms, comparing the atoms here. Similarly here, right, you can either take the hydrogen off of this oxygen or off of this carbon right here. It's going to be the oxygen. The carbon can't stabilize that negative charge very well. So it's going to be the oxygen because it's just a more electronegative atom. Also to note is that there is resonance between the negative charge that would be here and this pi bond. So it's going to be the first one. So on to this next page here. Says a balloon filled with helium gas is less dense than air and floats upwards into the atmosphere. When released, the balloon will rise till it pops, right? So you're assuming that the temperature is negligibly changing, right? Or essentially T is constant, is what you're assuming. And the change of moles in gas is negligible. So you're assuming N is constant. So if you think about Charles' law, P1, V1, or you could use Boyle's law where the temperature is constant. It's the same thing. I just use Charles' law and then eliminate whatever is a constant accordingly. And so P1 V1 is equal to P2 times V2. All you have to do is look at this relationship. So the volume increases, right? Or actually kind of spoil it, right? As the balloon rises, the volume increases and that's why it pops, right? So if the volume increases, it's because the pressure decreases. So as pressure decreases, the volume, oops, wrong one, the volume must increase. Right, pressure and volume, assuming temperature is constant and moles of gas are inversely related. So if everything else is constant, as pressure increases, volume decreases. As pressure decreases, volume increases. 22, it says the four compounds, HCl, zinc, ZnCl2, zinc chloride, and H2 are mixed in a reaction vessel and allowed to reach equilibrium. In this reaction, the temperature is held constant and all changes are small. Considering each change separately indicate the effect that the change has on the quantity in the second column, assume the reaction is reversible. Okay, so they give us the reaction here, which is nice. We're assuming that the temperature is constant, so we don't have to worry about any temperature changes, right, whether this is endo or exothermic specifically. And so we're just going to use Le Chatelier's principle here, right? So it says if we add zinc to this, so if you add zinc, you're adding something on the left side. Now, Le Chatelier's principle only really applies, right, to gases and aqueous solutions. You're not going to include liquids and you're not going to include solids. So if I add more of this solid right here, oop, what happened? The zinc is not going to have any effect. Right? The reason Le Chatelier's principle doesn't apply is it's based off the equilibrium constant stuff, right? And so solids and liquids don't affect the equilibrium constant. So adding zinc changes nothing. Next, it says increase the vessel size. So if you increase the vessel size, right, the volume is increasing. It's going to shift to the sides with more moles of gas. So the side with more moles of gas is going to be the right side, right? So this is going to shift to the right here. So what are we looking for? We're looking for the amount of ZnCl2. So if it shifts to the right, this is going to increase, right? Increasing the volume is the same as decreasing the pressure of the system. So if you increase the volume or decrease the pressure, it shifts to the side with more moles of gas. Just think of it as more space, right, for the gas to be in. If you do the inverse, right, if you increase the pressure or decrease the volume, it's going to shift to the side with less moles of gas. All right, 23 is a gas mixture of 52 grams, is 42.8% carbon tetrachloride and 47.2% xenon by mass. The container is maintained at 1 atm and 350.15 Kelvin. Find the partial pressure of xenon in the container. Right, so easiest thing to do would be like we did in old worksheets, would be to consider 100, oh, it's 52 grams. Never mind. We have that. I was going to do something else. But what we're going to do is just find the grams of each, right? These are both by mass. I was thinking kind of a mole fraction for the total pressure, but you're going to find the absolute partial pressure, not some ratio. Anyways, right, what you're going to do is find the grams of xenon and carbon tetrachloride in this, right? Fairly simple. These are by mass. You just take 52 and then you multiply it by their respective percents, right? Except as a decimal. So 0.428. Oops, that's 5. And this is 22.256 grams of carbon tetrachloride. And then you can find the other one. You'll get 29.744 grams of xenon. Right, I subtracted it from 52, or you could just do the percent. You're going to get the same thing. So now that I have this, right, I can convert these into moles using the periodic table. So can I move this? I'm just going to convert to moles underneath. So this turned into moles, where I'm just going to divide by the molar mass here. So carbon has a molar mass of, I'm estimating here, about 12. And then chlorine is about 35.5. I'm going to use 35.45. Right, and there's 4 of them. So when you convert this into moles, you end up getting 0.14. Let's just do 3 sig figs, 145 moles. For the grams of xenon, to convert that into moles, you just divide by 131. So dividing it by 131, right, this is 0.227 moles. All right. Now, we just have to figure out what the partial pressure of xenon is, right? So to find the partial pressure, you're finding the mole fraction of xenon. So you're just doing the moles of xenon, right, over the total moles in the gas. And then that's the mole fraction part. Right. And then the pressure part is just times the total pressure. Right, so the partial pressure of xenon is just the mole fraction of xenon times the total pressure. So this is, excuse me, 0.227 moles of xenon, right, over 0.145 plus 0.227 times 1 atm, right? That's what the container is maintained at. This gives you zero 0.61 because I rounded. So it's going to be C. So partial pressure, right? You just gotta find the mole fraction, find the moles of each, take the mole fraction. Mole fraction is just the moles of one thing divided by everything else plus that added together. All right, 24 is a container initially starts with 1 atm of argon, or of A, not argon, of A, which reacts to reach equilibrium according to the reaction below. Find the partial pressure of B, PB in ATM. So if you're looking at this, right, what you can do is essentially do an ice table. Now, why am I allowed to do this? So it says that this starts at 1 atm. I'm going to do ice like that. Why am I allowed to do an ice table? I thought you could only do that with, well, so it wasn't this test. I thought it was a different one, but you're allowed to use an ice table because the volume is kept constant, right? And the temperature is held constant. And so there is fluctuation in moles, right, for each gas, but these pressures, these partial pressures of each gas are linked to the moles. So you're allowed to use an ice table for that reason, just like how concentration is linked to moles directly, right, when the volume is not changing. Same thing is with pressure, right? The partial pressures are linked to the moles. I don't need to know how many moles of each are in this, right? I have the pressures. And I know that the temperature is constant. So that's why I'm allowed to use an ice table for this. So because again, partial pressures of each are linked to the moles of each. So since everything else is constant. So I have this 1 atm here, right? This is minus x plus x plus x. The end here, you get 1 minus x, x, and x. Now, you have your Kp, so your Kp is like Kc, except just written with partial pressures. So it's the partial pressure of products, right, over the partial pressure of the reactants. So in this case, Kp is equal to the partial pressure of B to the first power times the partial pressure of C to the first power over the partial pressure of A to the first power, right? They're all coefficients of 1. Now I have some values here that aren't ludicrous to plug in, right? So I don't have all these 1 times 10 to the negative whatever. I'm just going to plug them in, right? So this is 1 minus x. Oops, no, I messed up. This is going to give me 1 is equal to x times x over 1 minus x. I can't say that x is significantly less. Kp is pretty big, right? So I can assume that the equilibrium is going to shift considerably. And again, if you have a problem, that's going to be a bunch of 2.3 times 10 to the negative whatever. Leave these in terms of just variables, right? And then do it at the end. So like make something x, something else z or something, right? Or B. You could say B is the concentration of your base, or A for your acid. I don't know. But it will be it'll be very time consuming to just plug in all of the numbers. It's really easy to make a mistake like that. So you still can. I'm not saying you can't do it. I'm just saying it's easier not to do it like that. So you get x squared over 1 minus x. Now, if you multiply both sides by 1 minus x, right, you get, you get 1 times 1 minus x. That's just 1 minus x is equal to x squared. You get everything on the same side, right? This is a quadratic equation. And then you can't factor this, sadly. So you're going to have to use the quadratic formula, right? As I showed before, x equals negative b, negative 1, right? There's a 1 here for the b value, plus or minus the square root of b squared, that's 1 squared, minus 4 times a, which is 1 as well. There's a coefficient of 1. in front of the x squared times c, which is -1, all over 2 times 1. You go ahead and simplify this. You end up getting -1 plus or minus rad 5 over 2. You can't subtract the rad 5, right? Or else you end up getting a negative number, negative partial pressure, right? Because x is related to the partial pressures of B and C, right? I should have actually denoted this earlier, but that's the partial pressure of B. That is the partial pressure of C, and that's the partial pressure of A at equilibrium. So let me plug this in. And you end up getting 0.618. And so that, oh, no, I was like, that's a little too far. So that is your answer, 0.618. Yeah, and you're allowed to use that ice table because everything else is constant, and the moles are just directly linked to the partial pressures of each. All right, I'm gonna go to the next one here. It says, what is the total pressure? Oh, I need that. In the container at equilibrium. So I got rid of my ice table. That's unfortunate, but the partial pressure of A, right, I said is 1 minus x, which is 1 minus 0.618, right? So I can find that. That is 0.381 now, or 382. All I have to do is just add A, B, and C up, right? So the total pressure is just pressure of A plus the pressure of B plus the pressure of C. B and C are the same, right, as we did in the problem. And so 0.382 plus 0.618 plus 0.618. And then you get 1.61 or 2, sorry. Rounded incorrectly. That's your answer. All right, next page. Oh, thought there would be some more free response, but I guess not. So that's it for this test then. So I hope that helps. If you have any questions, just shoot me an email. Best of luck on the test, and I will see you tomorrow if you're in my class.